Hello there, this video is going to be on proof by induction. So proof by induction is a proof technique that involves 4 steps. The first is the base case. Then there's the induction hypothesis, which you have to come up with. Then there's the induction step, inductive step, INDUC. Inductive step, and then you have to write a conclusion. So most proof by induction questions are usually easy marks. So you'll need to write proof by induction for powers of matrices questions. Divisibility questions. And also, there's one more type. Powers of matrices, divisibility, and sums of series. So let's start with the powers of matrices question. A simple one would be to show that, let's say A, B, that's a matrix, and the rest of the columns are 0, and AB to the power n is equal to A to the power n, B to the power n, like that. And the rest of the columns are just zeros, but writing down the zeros every time, it's a bit of a pain. So sometimes if I leave places blank, it just means 0. So how would we prove this? So we need to write a base case first. In fact, this is true for n greater than or equal to 1, where n's an integer. So instead, we could write n is an element in the natural numbers, so that's the numbers from 1, 2, 3, and so on. So base case would be n equals 1. Just check if it's true for n equals 1. And that's simple as just saying a, b, power 1 is equal to a, b. And they could just put a little tick showing that's correct. In fact, this would not be okay. I just remembered, this would not be okay. You would have to write it out properly. So left-hand side is equal to a, b to the power 1, right? Because n equals 1. And that is equal to just ab, and that is equal to the right-hand side. And like this. And that would be a check. It's true for n equals 1. Now we need the induction hypothesis. So the induction hypothesis would be that this is true, that this statement is true for some number k. Suppose we'll call this statement P, just for instead, so we don't have to write it out again. Suppose P is true is true for n equals k. Okay, and now we have to do the inductive step. An inductive step, you need to show that P is true for n equals k plus 1. So how can we do that? Well, let's just write down a b to the power k plus 1. And this is equal to a b to the k times a b. That's just how matrix powers work, and you could write in either side. You could write these in the other order if you wanted to. That'd be absolutely fine, because they're the same matrix. So we can use in the induction hypothesis on this part to say that this is equal to a to the k, b to the k, because we know that P is true. We're supposing that P is true for k, for some number k. But k is also in the natural numbers, because we're only proving this for the natural number n's. So n equals k, and this is by the induction hypothesis. Right, now we multiply these two matrices together, and we can just do normal matrix multiplication. So what we have would be a to the k plus 1, b to the k plus 1. And that now we could say, thus P is true for n equals k plus 1. So we've shown, and sorry, this is the conclusion. We've shown P is true for n equals 1, and if P is true for n equals k, then P is true for n equals k plus 1. Therefore, by the principle of mathematical induction, P is true for all